Hello class, today I'll be going over my video for the Physics Lab 4, which is circuits. So, as an introduction, circuits are closed paths where an electric motive force, in this case the voltage from our two 1.5 volt batteries, forces a current of electrons along a wire in which it experiences a voltage drop. In a round trip along a closed circuit, the change in voltage will be zero. Ohm's law states that the change in voltage equals the current times the resistance, which you can see in these equations up here, which are just different forms of Ohm's law. Now, this lab will involve building circuits with resistors, capacitors, and light bulbs. And ammeters will be wired in series to measure the current, and voltmeters will be measured in parallel to measure the voltage. When in series, resistances add together to create a total resistance for the circuit, which determines the current. And here you can see a circuit in series where there is a constant current flowing throughout despite the different resistors. So the system for this lab will consist of any element of the circuit. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, and to use multimeters to measure the actual values of conventional current and potential difference in the circuits, and to examine the behavior of ohmic resistors and capacitors. So a preview of our results are that the measured current was at 0.01 amps, and the measured potential differences across the 47 and 100 ohm resistors were 0.92 and 2.94 volts respectively. So our prediction for the current measured in locations I1 and I2 would be the same, as this is a circuit that's wired in series. So we use Ohm's law to find that the current equals 0.0204 amps. And as said before, the current on both ammeters should read the same. And the ammeters will read negative when the connection is reversed because the current is directional, and it will read it as going backwards when the ammeter is plugged in reverse. So when we actually go to the experiment for this part, the measured current was 0.01 amps and not 0.02. And this is likely due to inaccuracies of the ammeter because the milliamp setting wouldn't work during the actual lab portion. And there may have been resistance from the wire or the ammeter that wasn't accounted for and lowered the actual current. Both ammeters did give the same reading though, and the ammeter read negative when the connection was reversed. So here you can see the measured voltage changes across different parts of the circuit. In the round trip, it was very close to zero, but was a little bit off, most likely due to the fact that the voltmeter can only read to a few decimal places. The ammeter reading doesn't change with the addition of the voltmeter because the resistance of a voltmeter is significantly higher than the resistance in the circuit, to the point where a negligible amount of current flows through it. So a question is, if we connected the voltmeter across the 100 ohm resistor again, and note what the ammeter is reading, and we got 0.01 amps, so the same as it was reading before. If we put an ammeter around the 100 ohm resistor wired in parallel, the current would just flow through that ammeter, and thus it would read a higher current in the other ammeter, as the current no longer has to go through a resistor, and it can just go through something that has virtually no resistance. Here are resistor calculations using our measured current and the voltage changes across the resistors. And as you can see, there is a significant difference between what was expected and what we calculated. And this large error is most likely due to the inaccurate reading from the ammeter, as it varied wildly from the expected value of 0.02 amps. So, onto capacitors. When connected in series with the capacitor, the light bulb gradually decreases in brightness until it goes out. When the battery is disconnected and the capacitor is connected to the bulb lights up for a short amount of time before dimming and going out again. So when the capacitor is charging, the current is slowly decreasing until it hits almost zero. When the capacitor is discharging, the current is flowing in the opposite direction as before and decreasing magnitude until, like before, it approaches zero. The time it took to charge the capacitor with a 10 ohm light bulb was 12.95 seconds, and the discharge time was 10.98 seconds. For the 20 ohm light bulb, the charge time was 21.85 seconds, and the discharge time was 19.22 seconds. Let's go over some sources of error. As said earlier, the results from the ammeter were significantly off from what was expected, and this led to the calculated resistances for the resistors to be inconsistent with their actual values. The wires and ammeter also provided small resistance values, which wasn't calculated for in theoretical calculations. However, these should have been pretty negligible, as the resistance values were pretty small. In terms of timing the capacitor charging and discharging, this was pretty subjective, as you had to judge when the light bulb was fully out or still had a little bit of light left inside of it. So, under our what-ifs, compared to a stimulated ammeter, the actual ammeter had a small amount of resistance to the circuit, and its accuracy was questionable, as we weren't able to use the milliamp setting. For the second what-if, the capacitor would charge faster if there was no resistor in the circuit.